Okay, good morning. Thank you very much for introduction, and thank you very much for giving me this opportunity. My name is Naoyuki Tamura. The director Miyazaki was supposed to be here, but there is a meeting in Japan ongoing right away. That's a Japanese version of WAS and kind of thing. And then he has to be there, I think. So he told me to come here. So thank you very much for this opportunity. And I'm very new to the Keck community. So I thought I'd talk about myself quickly, first of all. I joined Subaru a year ago or so. So I'm still a bit new to the observatory as well. But I've been working for Subaru quite some time, since I was a student in Kyoto and I was postdoc in Durham. I was part of the team who developed ECMOS, the former generation fiber-fed multi-object spectrometer. And then I came to Subaru and I stayed there, worked for 7 years as a commissioning scientist after all. And then I left Subaru, but that was actually to work on PFS again for Subaru. And then I've been a project manager and a systems engineer for more than a decade now. And then came back to Subaru last year. And then my main role is now to take care of the overall instrumentation. So let me focus on a few highlights on the instrumentation side of Subaru. Okay, so I believe PFS deserves taking the first seat of those highlights. PFS is a very wide field, highly multiplexed, wide wavelength coverage spectrometer with prime focus instrument feeding the light from the sky into the instrument. Metrology camera system at the classical focus to look at the prime focus focal plane and measure the fiber tip positions there. 60-meter long fiber cables transmitting the light from PFI to the spectral system that equips 4 identical spectral modules and generate about 2,400 spectral images. As some of you may know, the PFS has been in the commissioning process for quite some time now, since metrology camera system arrived at the telescope in 2018. And then the other components followed, and then we managed to start on telescope tests in September 2021. I should stress here, because I'm in Caltech, that we all appreciate the critical commitments by the team from Caltech and JPL as part of the PFS collaboration for the fiber positioner and positioner module developments. And then still the integration continued. And finally, last month, we see all the hardware components in place and operating at the engineering observation. So just to recap these achievements in a different way. So this is where we were 2 years ago when we managed to observe many bright stars over the focal plane as we intended. And then so 600 fibers, yes, 600 fibers are horizontally arranged, and then the wavelengths are dispersed vertically. And these many vertical lines are the continua of observed bright stars. And 2 months later than that, we managed to commission the second spectral modules and doubled the multiplicity from 600 to 1200. And it took a while after that, but and also the geometry is now rotated by 90 degrees. So now the fibers are arranged vertically and the wavelengths are stretched horizontally. But this is what we get now from every single exposure, about 2,400 spectral images all the way across from 380 nanometers to 1260 nanometers. And this is the summary of the fiber configuration, fiber positioning accuracy. So when we try to understand this performance, we do so-called the raster scan operation, where we configure the fibers in such a way that we think right onto the targeted object. And then we take a spectrograph exposure and then dither the telescope a little bit, and then take another exposure, and we repeat this process until we complete a dither pattern around the nominal bore site. And then we can make a 2D flux map around each fiber and understand how much offset there is between the fiber positions and the real targeted object positions. And this left-hand side plot is the one example of the quiver plot showing the offset of each fiber from the real targeted position. And this is the cumulative distribution of those offsets. And then the right-hand side, this is the plot of the 95th percentile of those offsets across several nights of the data sets. And this indicates that the typical error of the fiber positioning accuracy is 20-30 micron, and the best case it's less than 20 micron. That corresponds to 0.2 arcsecond or so on the sky, compared to 1.1 arcsecond on average of the fiber diameter. And this fiber reconfiguration process can be completed in 130 seconds typically. 120 seconds is actually the best record. And these are actually great. Sorry, okay. These are actually great, but the team is still working hard to see if these can be further improved. And also in particular, these can be stabilized in such a way that these can be always as good as the best. And this is about the measured throughput. So on the left-hand side, the measured throughput is compared with other spectrometers. And then on the right-hand side, this is a comparison between the one of the recent throughput models versus the measured throughput. And still there are areas where we need to improve the accuracy. For example, the edges of the wavelength coverage. And this needs updates according to the newest data. But overall, this is quite encouraging. And this is these are examples of pre-processed calibrated spectra of faint galaxies around redshift about 1. And you can see not only strong emission lines, but also you can see continuum and also absorption feature clearly. This is also quite encouraging and reassuring to us. Okay, and then these statuses of the commissioning processes were recently reviewed. And then PFS was advertised to be one of the open use instruments from the next semester S25A. And I heard that quite a few proposals have been submitted. That sounds a bit scary, but that should be a great start. And as some of you may know, the Q observation is basically the nominal operation mode of PFS, where the target object from multiple different programs share a single field focus. And that we believe that is the best way to exploit the very wide field, the very high multiplicity, and also a dynamic reconfiguration process this instrument can do. Okay, so on top of this current Subaru's instrument lineup, as I presented earlier, PFS is upcoming. And then I will try to quickly talk about two more updates, which both are associated with the adaptive optics. So first one is about the upgraded AO system. So we used to be using 188 element deformable mirror, but we replaced that with a new one, which has more than 3,000 elements. And because we also managed to commission recently the new wavefront sensor in the near infrared, which is compatible in terms of the number of elements with this AO deformable mirror. So we managed to demonstrate its performance of the 3,000 element already at its first light in June. And right now, in parallel to these efforts, the team is trying to upgrade also the visible wavefront sensor to be compatible with these 3000 elements. And the last update is on about the Ultimate Subaru, which is a GLAO-assisted wide-field instrumentation, employing the adaptive secondary mirror and also a wide-field instrument on the classical focus, usually basically operating on bright nights. And this is the timeline, at least at the point of a couple of months ago also. So hopefully there has been no large slip since then. But anyway, the designs are getting matured, and also some parts are already being manufactured. And fundraising for the wide field instrument, wide field imager, recently succeeded. And then the system integration on the telescope should be supposed to be started in a few to several years. And we are coming to the mid-2020, and I think we are reasonably doing well. But always it can be too late to start thinking about futures. So right now, we are HSV. Haven't said anything about HSC, but it's been working well. PFS is upcoming, as I said, and Ultimate is catching up. And because of the AO upgrades, partly, we should be doing well enough for the extranet sciences and so on. So yeah, we are doing reasonably well. But we should think about the futures, and then brainstorming discussions are underway at various levels. The workshop we had a couple of weeks ago was part of it. But discussions can't be easy. There are many variable directions. There are many variable demands, and we are in the middle of them. And but we need to keep and think, keep working hard and thinking hard. And then and also there are some headaching situations such as money and people, as you may know very well if you are involved with management. But yeah, we need to keep working hard, and then we need to come to some coherent strategies because future is approaching, and then it won't stop. Okay, and I'll put this slide as a summary, and then I'll take questions. Thank you very much for your attention.